Adomaitis. I'm a professor in the Chemical and Biomolecular Engineering Department, and I have an appointment, a half-time appointment here at the Institute for Systems Research. I also have appointments in the Maryland Nano Center and the University of Maryland Energy Research Center. And my background is in chemical engineering. Both my degrees are in chemical engineering. I received my PhD at the Illinois Institute of Technology in Chicago, and I also received my BS at the same university. And my background is in process systems, computational work. After I received my PhD, I spent 2 years as a postdoctoral researcher in the chemical engineering department at Princeton University. And then I came to the Institute for Systems Research. At that time, it was actually the Systems Research Center. I came here as a postdoc in the 1990s, worked as an assistant research scientist for some time, and then eventually joined the chemical engineering department here at Maryland. And so my background, as I said, is in process systems. I'm a systems person. I'm primarily interested in mathematical modeling and computational techniques as applied to chemical engineering systems particularly. I'm interested in thin films. The work that I do is in thin film technology, which seems very specialized, but actually has quite a few application areas. Originally, this work was based primarily in microelectronics device processing, and subsequently it's grown over the years to include topics in solar energy research, and most recently we've begun a nice collaboration with the NASA Goddard Space Flight Center, and we're looking at developing thin films for applications for spacecraft systems, optical components, and various other things, because it makes sense to develop thin film technologies for these applications, because weight is very critical in these applications. In solar energy, the type of work that we do in thin films is in the development of photovoltaic cells, in other words, solar cells, various aspects, including creating the solar cells themselves, optical coatings for the solar cells, and protective coatings as well, and developing new technologies, for example, developing semiconductor materials, thin film semiconductor materials that can be used to harness solar energy to split water directly into hydrogen and oxygen. And so all of these fall under the categories, as I said, of thin film processing. The challenges to me are trying to understand these processes at a very basic level. So it's kind of an exciting time to be doing this type of research, because the work has really gotten to be very much at the atomistic and molecular scale, trying to understand the deposition processes from this very fundamental level, understanding the chemical reactions, using new mathematical techniques in order to understand the rates at which these chemical reactions take place, the specifics of the chemistry that's involved, and most importantly, trying to be able to compute how fast these chemical reactions take place, because ultimately, as engineers, what we're interested in is in the optimization of these processes, trying to create very large-scale chemical processes by which we deposit these thin films in as efficient a manner as possible. And so what that brings to bear is a lot of systems engineering tools, and that's why we're here working in the Institute for Systems Research. The idea is that we take these fundamental physically based models and try to use optimization and, as I said, a lot of sophisticated mathematical modeling techniques in order to be able to create the useful industrial processes by which these materials are created.